Hello everyone. In this session, we are going to see the basic information on the batteries. First, we need to know the history of the batteries. I have listed here the historical overview of the batteries. Batteries have existed for more than 2000 years. The earliest known example date back to 250 BC, Baghdad. Okay, where this Baghdad cells functioned as a galvanic cells. In 1800, Alessandro Volta built a first modern battery called voltaic pile. Later, in 1834, Michael Faraday developed the laws of electrochemistry, establishing the link between chemical and electrical energy. In 1866, Lichens developed the zinc carbon battery, which is still used today in the primary batteries. In 1859, Planck invented the rechargeable lead acid battery. Later, nickel cadmium batteries were developed by Younger and Edison. Now, the modern portable electronics where the nickel metal hydride batteries and lithium ion batteries are used, and nickel metal hydride batteries are invented in 1990 and lithium ion batteries in 1991. Then what is the difference between these batteries, how they are evolved over the period of time? Okay, main difference is some batteries are reusable, some are not reusable. That we're going to call it in a technical term as primary and secondary batteries. Now here you can see in this slide primary versus secondary batteries. The batteries are classified into primary non-rechargeable, secondary rechargeable batteries. Primary batteries are non-rechargeable, secondary batteries are the rechargeable and focus on the battery management system. Where rechargeable batteries include lead acid, nickel cadmium, nickel metal hydride, lithium ion, lithium polymer. And primary batteries include zinc carbon, alkaline, zinc air, and lithium ion. Where these primary batteries are a single use, where the chemical reaction is not reversible. But in case of secondary batteries, we can reverse the chemical reactions so that it is rechargeable. Now, we need to see the important battery definitions. Okay, now here you can see first one is cell, battery, energy density, specific energy, C rate, cycle life, cutoff voltage, and self discharge. Here a cell is the basic electrochemical unit. Okay, battery may consist one or more cells. Then energy density refer to the energy per unit volume. Then specific energy refers to energy per unit weight per kg. C rate indicates charge or discharge current relative to its capacity. Now coming to cycle life, which indicates charge or the number of charge discharge cycle before capacity drops to 80%. Okay, now cutoff voltage is the voltage at which the discharge stops. Self discharge is the capacity loss during the storage. Okay, now these are some important battery definitions that we are going to use wherever we are using the cells and batteries. Okay, now we are going to see the battery design. Now in the battery design, there are two main designs. Actually, there are three: cylindrical, prismatic, and pouch. Here we are considering the two main designs, cylindrical and prismatic cells. Okay, battery performance depend not only on the chemistry but also on the design. Cylindrical batteries used rolled electrodes. They allow high current. Prismatic batteries used stacked electrodes and better utilize space in portable devices. Okay, and different battery types are optimized for different application. Depend upon the application, we are going to use the different designs. Okay, now uh, coming to the comparison part of major secondary batteries, here you can see I have listed different battery chemistries. SLA is nothing but the sealed lead acid. Here, nickel cadmium batteries are robust but have memory effect and environmental issues. You can see, okay, cycle life, self discharge. And nickel metal hydride batteries offer high energy density but are more sensitive to over voltage. Lithium ion batteries provide high voltage and high energy density but require strict safety controls. SLA batteries are low cost but heavy. So depend upon the different application and cost involved, we are going to use different battery chemistries. Now, how these battery are going to operate? In general, we are going to see the operation of the battery here. Now, general operation of the battery. Okay, where battery converts chemical energy to the electrical energy. Okay, battery operates through redox reactions. At the anode, oxidation occurs and electrons are released. At the cathode, reduction occurs and electrons are accepted. Okay, where electrons flow through the external circuit and ions move through the electrolyte. This is the basic operation of the battery. Here you can see positive electrode chemistry is listed here, negative electrode chemistry is listed here. Overall chemistry, chemical reaction is shown here. Okay, A shows us the during the charging, B shows during discharge. Okay, now next here equilibrium potential and thermodynamics. When there is no current flows, the battery in equilibrium, the forward and backward reaction rates are equal. So there is no net current. At this condition, the battery voltage is called in equilibrium. Okay, and this voltage is called equilibrium potential. The Nernst equation here you can see tells us the equilibrium voltage depends on the ratio of the activities or concentration of oxidized or reduced species. Since the concentration charge during charging and discharging, the equilibrium voltage depends on the state of charge. There is also a direct relationship between battery voltage and Gibbs free energy. The equation here, delta G equals minus of Nf times E, which shows that the battery voltage represents the chemical driving force of the reaction. So at the equilibrium, thermodynamics determines the voltage. Now, however, when the current flows, the battery is no longer in the equilibrium. The actual voltage deviates from the equilibrium value due to the overpotential. Okay, then here you can see when there is no current flows, the battery voltage equal to the equilibrium voltage given by the thermodynamics. But when current flows, the system moves away from the equilibrium. The difference between the actual voltage and the equilibrium voltage is called the overpotential. This overpotential has two main components. First one is kinetic overpotential. Second one is diffusion overpotential. This kinetic overpotential, this is due to finite speed of the electrochemical reactions at the electrode surface. The see here, the Butler Volmer equation describe this behavior. If the exchange current is small, the reaction is slow, and larger overpotential is required to drive the current. The second one is diffusion overpotential. When the current becomes large, reactants near the electrode surface are consumed faster than they can be supplied from the bulk electrolyte. Okay, which creates the concentration gradient. When the surface concentration approaches zero, the reaction becomes diffusion limited and current cannot increase further even if the voltages increases. Okay, so the kinetic overpotential is reaction rate limited, while the diffusion potential is mass transport limited. This session covered the fundamental electrochemistry behind the batteries and the practical factors that influence their performance. Okay, understanding the equilibrium voltage, overpotential, and diffusion effect, where this is essential for designing safe and efficient battery management system. Okay, in next lecture we are going to discuss about the battery voltages and its application.